Yeah.
So we can change the orientation, and I can change the penetration depth, like this sometimes. A finer thing is sometimes they purposely damage it and turn it into amorphous and cause it to recrystallize. But here you can see the damage from the implantation that can happen, light versus heavy ions and so forth. But generally they can master it very well and use it to deliver known doses of things. And so the beauty of this, you'll see this come full circle when we get into transistors, where the ion plantation is going to come down and deliver a specified dose between the source and the drain, and that's going to be very important. You don't know why yet, but it's going to come out to be very important. So this is a really nice way to put the finishing touches on your transistor. And I can use lithography and so forth, where I've got big organic change with photoreceptors on it and an ultraviolet light, and I can make photoresist where it's a hollow hole here or a pillar, and that allows me to micro machine the semiconductor in where this organic stuff is considered, this photoresist is considered sacrificial. So I put it on, pattern it, and it allows me to etch, diffuse, do all kinds of metallize, do all kinds of things to the wafer where it's only in certain regions. Like I could do some etching here, and this photoresist would act like a mask to protect the other areas. And that's how I build up my devices. I use a mercury lamp, and I cherry pick one of those ultraviolet lines that's tuned to the photoreceptor on the resist, and I get my photoresist profiles. So I can micro machine this. And then once we have those substrates, so diffusion and implantation are sort of a side set of ways of doing impurities into pre-existing wafers. But the more elegant way is to do thin film epitaxy, to take the substrate and to do some Tetris, and slowly grow up my crystal. And this is the more elegant way where I can build multi-layer devices, multi-layer crystals, multi-layer structures. And so I can go back to my phase diagram, and I can do gallium arsenide liquid phase epitaxy. And I think I gave you the example. Here's liquid phase epitaxy. What if I wanted to make a sugar crystal for my coffee stir? I wanted to make a new coffee stir for Starbucks for Valentine's Day, and I could put a white, pink, and red sugar solution in here, and I could just pull this boat back and forth, and I can make a rainbow color, piece of sugar rock candy. But here we're making a crystal, maybe a semiconductor laser. And CVD is where you're inputting gases, and the wafers are standing up, and the gases are pyrolyzing. They're as they come into this hot furnace, these organometallic materials decompose, releasing the material we want. So I might be able to deposit silicon using silane. So the silane decomposes, some hydrogen pops off and gets pumped away. Or I could deposit some gallium arsenide with a trimethyl gallium and an arsenic gas, arsine gas. Trimethyl gallium and arsine. So here's another way you're doing, maybe you're giving a little heat, some radio frequency, and so you're heating these up. So these are sitting in there in this hot bath, and you're bringing in the gases that you're interested in. This is doing silicon vapor phase epitaxy. This is the more elegant. This is probably how a lot of your LEDs are made, with a MOCVD reactor. So it's using these metal organic chemical vapor deposition. So it's using trimethyl gallium. So it's a gallium with 3 methyl groups, and trimethyl aluminum with 3 methyl groups. So here's your arsine. So trimethyl, is a CH3, and the arsine has 3 extra hydrogens there. So you can see the beauty. Trimethyl gallium has 3 of these, plus the 3 hydrogens from the arsine, and so they get together and I make 3 methanes, right? And so the methanes are fairly inert and they get pumped away by the vacuum system here. So, but I'm left with the gallium that came with the trimethyl gallium, and I'm left with the arsenic that came with the arsine. So I get this innocuous methane that I kind of scrub and take away. But I get my host matrix, and that's what it looks like. There's one sitting on West Campus in Kinnear, by the way, at Nanotech West. It was part of a big project 6 of us faculty were on. Here's MBE, molecular beam epitaxy from Mort Panish. He's retired. He used to be in my department, in my lab, my extended lab. This was invented though by my boss's boss, Al Cho, co-invented. And so this is a small cartoon of it, but you're basically taking the raw materials, no longer these gases, but you have the raw materials in their elemental form, gallium, dopants, arsenic, and you're evaporating them from first principles. And they're going to the heater. And this used to be called, in its early days, it's now called molecular beam epitaxy, but in its early days it was called the 3-temperature technique, because you had gallium at 1 temperature, arsenic at the other temperature, and the substrate at the 3rd temperature. And remember, temperature and time, if gallium and arsenic rained down on a cold substrate, I would get an amorphous crystal, and it would be of no value. But because this is heated, the gallium and arsenic come down, and they have an opportunity to assemble. That was what that Reed oscillation and Reed diffraction pattern and all that was that I was showing you earlier. And so they move in a correlated manner. In fact, as an aside, this is not testable, but each of those atoms actually comes down and probably hops 10,000 times before it finds its resting place. So you can build beautiful multi-layer structures. We can grow with atomic precision. Yeah, there's a better rendering of it. The beams coming in, hitting the substrate. And that's that Reed gun coming in for that diagnostic at an oblique angle.
So what phase are these coming in as? You said the other one was gas?
Yeah, and this is now an elemental, or often to give it some of its molecules, because the arsenic doesn't come off as arsenic, because usually if it just you heat it up, it comes off as 4 arsenic atoms. It comes off as little clusters. So they call it molecular beam rather than atomic beam. That's what it actually looks like, a big chunk of stainless steel. Technically, it doesn't need to be in a clean room because everything's hidden inside this vacuum chamber. And that's segment 1. So that took a little longer than I thought. Segment 2, I'll be upfront with you. Segment 2 is probably less of a testable material because this is what I'm beating you up on for the take-home computer problem. So you kind of know already what I said as far as diffusion is a way to introduce impurities. So just know that there's kind of 2 techniques. One's the constant source, and the other's the limited source, which is a 2-step process. You pre-deposit, followed by a drive-in. And that's probably, a lot of this, the different impurities and all that, and so forth. Maybe know the fact that why did I do the diffusion at a hot temperature? Well, at the hot temperature, it opens up the crystal, so it's kind of ready to receive. It kind of introduces these vacancies, so that impurity can percolate through the crystal. So if I didn't heat it up, it would just be fairly inert.